Hello, everyone. My name is Marina Radulaski, and I'm an assistant professor at the University of California in Davis in the Department of Electrical and Computer Engineering. It is a pleasure to be here virtually supporting the NSF Engineering Career Workshop 2022. I have a lot of respect for what National Science Foundation does in terms of supporting junior faculty in working on their tenure track projects and establishing themselves as eminent researchers. My career project is called Scalable Quantum Photonics based on color center integration with angle-etched silicon carbide devices, which is quite a specific title, as I was encouraged to name it by my program officer, Dominique Dagenet. The project started in February 2021, so we're a bit more than a year into the project. And today I will tell you about a project in a way of structuring the story, hitting those important marks. And then I will move to the advice section and give a few more pieces of information of how I approached applying to this project. Before I start, I should mention I applied twice, so I got this project in my second application year. And there are also nice things to learn along the way. Now, the first thing I want to point out is the area of my research, and that is quantum information technologies. This is the area that has three main research growth directions: quantum internet or quantum networking, quantum simulation and computing, and quantum sensing. Now, the next is the system that I study within this area, and those are color centers. Color centers are defects in semiconductors. So basically, if you have a lattice of a semiconductor and then an atom is missing, or there's another atom instead of it, we have a defect that is formed and attracts, or rather localizes, electronic orbitals. So in a way, it behaves as a quasi-atom with its own orbitals, where electrons can hop between them, emitting single photons, and also having a spin of the defect that can be entangled to those photons. So that is the key of the color center application in quantum technologies. Color centers also have attractive properties in terms of long coherence time and entanglement schemes that can be used in various applications. Now, the impact of research on color centers is really in all of the quantum technologies, which is why we sometimes say that color centers can be used to build out the quantum technology backbone. So in the quantum internet, it is more the photonic side of things, the emission of single photons, indistinguishable photons, and spin photon entanglement for quantum repeaters. On the quantum computing side is the generation of cluster entangled state, which is a path toward measurement-based quantum computing, which is a different path of computing than currently explored in research and industry. Quantum simulations are also a technology that can be supported by color centers through their integration with photonic devices. And quantum sensing is already a successful area commercially of color centers, where they are used for nanomagnetometry and nanothermometry. Now, the approach that we take in this research is integration of color centers with photonic devices, or the area called quantum nanophotonics. Now, this is important because integration with photonic devices increases the efficiency of quantum processes that color centers provide, and that way can bring some processes from just the proof of principle to really practical applications. Another important part about the integration of color centers with photonic devices is that they can provide integration of many devices all on one chip. And so that can also help with scaling these technologies to very complex systems. Now, Where does this research fit in the ecosystem of quantum technologies research and color centers? So for that is a question that I also got both from the program officer as well as from my colleagues who are supporting me. And I decided to organize that answer in a table. So what we see here is different color center systems and how they were studied in optical properties and in the photonic integration, which is what I want to pursue through this project. And clearly it shows where this proposal is placed, as well as that area has not been studied by other groups yet. Another cool thing about using such a spreadsheet is that you can use it to also show a bit of your track record. So I put in bold the collaborations that I worked on as a PhD and postdoc. And so it really, in a nice way, shows where you're coming from and where you're trying to go next and how that has not been addressed before. Now, another thing that was praised in the review was that this project uses a unique resource we have at UC Davis, and that is an ion beam etcher ordered and specialized or specified for silicon carbide etching. This tool is rare to find in clean rooms. Very few universities have it, and then also those that do have it have often lack of gases needed to etch silicon carbide. And so this really showed that the unique position that we have, both with my research background and in terms of technology, to bring this research line to fruition. Now, here again comes another table, and this is the only one I have left, is what is different about using this tool. And so here is really the geometry. We are going for angle etching, which means triangularly shaped devices. And usual etch is the rectangular etch. Here we're showing some examples of quality factors achieved with these different approaches, using diamond as a comparison because that system is more studied, and then silicon carbide as the system we actually want to study. So again, we see that the area we want to look into is has not been served well so far. And then also that there is track record on different papers that I've been working on in my previous part of the career. I mean, professional career. So yeah, again, table came in to summarize multiple paragraphs that I would write and the reader might get lost with. Now, of course, you don't want to overdo it. I took 2 of them. I don't recommend doing this for more than 2 or 3 points you want to make. Okay, so now I want to show just a little bit of results that we got in the first year with this approach. So this area has not been really studied, how light propagates in triangular silicon carbide devices. And so we were able to study what that behavior is like and model how light couples to a single mode, which is very important for quantum applications. You don't want your photons, your light to travel through multiple modes and then you don't know where to collect them. And this research then went on into an international collaboration, and we had this recent publication in Nature Materials where we showed that in these fabricated triangular waveguides, color centers maintain their properties. So this is an important part in integration, that while fabricating the devices, they don't get destroyed. And so these are some of the things we didn't know when I was writing the career application, which made it a bit more high risk, high reward. And now we're slowly de-risking this and getting through our engineering part toward the fundamental science, which is the core of National Science Foundation research. Now, as I mentioned, fundamental research is really important. Even though this is engineering division, I was encouraged by my program officer to specify what is the fundamental science we are going to learn here. Okay, great, we are making devices that no one else can use. Sorry, no one else can develop, but someone can use, and we can use them also to discover something about nature that we didn't know before. And so there comes the piece about the multi-emitter cavity quantum electrodynamics, a regime that hasn't really been studied in the way that that uses only several color centers in a nanoresonator. And so that is the fundamental piece of the story, which also some part is achievable in experiment within the lifetime of the project, which is 5 years, and then some is more futuristic, like these arrays that we are proposing for quantum simulation. Again, this is a publication that we recently sent for review. Now, so we've gone through the field, the system, the approach, how it's unique, and why are you the person to deliver it. So the engineering, the fundamental science. And now let's go to the educational plan. Very important for NSF career. So here I have a few pieces of advice, but also how I thought about this. And this is something I learned between the year 1 and year 2 of application. In my background, I have pretty strong track record with education and outreach. In my PhD and postdoc, I did huge outreach efforts in elementary and high schools and middle schools, reaching out to 10,000 students, many of them underrepresented in STEM. And then also I hosted and produced a podcast, a science podcast that reached to 80 different countries. So that's what I was starting with. But all my contacts were at my previous institution when I just started my tenure track. So while I could come up with really good program of what I would like to do, I didn't have as many relationships. So I was making those contacts as I was writing, but basically, if I was awarded the career that year, I would need to start everything from scratch. So the thing that I took the second year was building on my track record. So I looked at the projects that I worked on in previous years since joining UC Davis, and those were a little bit different than what I was initially proposing. So there was a software package that my students and I were developing through a quantum hackathon that can be used in classroom. And that seemed like a really cool project that if it would grow, it would have much more impact both to our students and externally. So I decided that should be one of my proposing projects. And then another one had to do with education in quantum technologies, but not in terms of coursework. Coursework I already have to do as a part of my job, but rather starting a quantum journal club and making a community and culture around quantum information technologies at UC Davis. And there I could point to my outreach efforts on this international quantum career panel that was broadcast to the whole world, that had thousands and thousands of views on YouTube. So that was helpful to show that I actually am qualified and have experience in doing such things. Another one was reversing gender bias STEM, which again, even though I knew I had years of experience with, I needed to prove that I can do it at UC Davis. So within this first year, I actually worked with a local high school with their group of students interested in STEM. And so I could point to that and as a relationship that I can build from, and specified more toward the goals of this project. And finally, broadening participation, work with institutions that serve very broad communities with events that are open for everyone and that have history of reaching out to groups that are underrepresented in STEM. So that was the fourth part of my proposal. Now, it's important to consult literature while you're writing educational plan to support that your vision is viable and that there's also either a local or national need for such an effort. You should avoid things that are already part of your job, like developing a new course or mentoring students. Clearly, to do your research, you need to mentor students, so that will probably not cut it as a innovative enough educational plan. To show that you know what you're working on and who you'll be working with, you should specify either the programs that you're working with or institutions that you'll be collaborating with, and take the letters from those institutions. So in my case, I got letters from schools and programs I'll be collaborating with, and Center for Educational Effectiveness, which is an important player in the proposal because each of these sub-projects needs to have an assessment plan. So I think that this is also an important thing, have a little subtitle, assessment plan. And so that is something that's best done with professionals. And so for that reason, I partner with Center for Educational Effectiveness at UC Davis. Yeah, I'd like to point out that a lot of this research and outreach is actually done by students, right? It's not just the PI. And it is important who's on your team and that you have people who are able to carry out those projects. And so even though career supports pretty much one PhD student, it is by engagement with the topic that other students are impacted as well. And so here you can see the team of my PhD, master, and undergrad students who took part in either in some parts of research or some part of outreach and really benefited from this opportunity. Now, the accomplishments also come in nicely because NSF's career builds your profile and you get more attention, and you also get means to do this cutting edge research. And so my students got a summer research fellowship because they were working on a promising project. And so the department wanted to support that vision as well. And then an undergraduate student who worked on this area was also finding himself on job market and finding jobs that a year before working with us, he couldn't even apply for. Moreover, he was able to augment the lack of master thesis or master education on his CV by having done research with us for a year. And so that is also a great example of impact that NSF Career has on building workforce, and definitely quantum ready workforce is so important at this time for our nation. And on the other hand, as I mentioned, PI's prominence also increases with NSF Career. So in past year, my group's research was recognized with the Women in Quantum Award for leading researcher in 2021, ETH Zurich Pauli Center Research Visitor Award or Fellowship, where I was able to start with the ideas from NSF Career Project, but then build them into a whole other area, and then go out and with those ideas win a Google Research Scholar Award, which is then just proliferating the research toward new areas. I'm pretty proud of that progress that was seeded by NSF Career Support. And then in terms of the group, we've been invited to 18 talks. We published 6 papers. There's a 1 preprint waiting for review, 11 conference abstracts. So quite a nice contribution to the community. Now, let's go to the advice part. So I mentioned that I applied twice for NSF Career. So the first time I just started my tenure track, and I saw that there is NSF career deadline coming up, I called up the officer and asked whether my topic will be a good fit. To be specific, I emailed the program officer with a one-page summary, and then asked if we can get on a phone call and asked about whether my area fits. Now, there were interesting questions that I was faced with, not just about research. So the call lasted probably an hour. So there were questions about research, about why this is important, how it's different from others, how do we plan to implement it, and so on. But then there were questions also, why do you think this fits with the engineering? Your topic is interdisciplinary. You could go also to mathematical and physical sciences, MPS division. But there I was actually able to discuss how this project is really focused on engineering of these devices, and that its home really is in the engineering division. Also, I got to ask how the proposals are going to be evaluated, and here's some tips and tricks about what a panel will care for. Then I was thinking about what to propose. The first two ideas came in easily, but I felt also pressured to have 3 ideas because that's a golden rule. I would advise you not to think about it that way, or rewrite what you have into 3 goals if you really care about it. But yeah, I had two pretty solid parts of research. And then for the third one, I wrote something that I came up with pretty late in the process, didn't get to think it through. And actually just a couple of weeks after submitting career, I realized that some parts of it might not be feasible. And I was not the only one to catch that. The committee, the panel also criticized that part of the proposal, which didn't get awarded. But at the same time, I got feedback that the general area of research as well as educational component are solid. So I knew that for next year, I just need to address this part or maybe come up with something to replace it. So I made sure that not too much time passes since that rejection to again, get on a call with the program manager to hear insights, because the panel, sometimes there's not every detail is captured. And so the program officer could give me an advice on what to change for next year. I also heard that it was quite a competitive proposal. So that was all pretty encouraging. And this time I made sure not to work on it till the last moment. I actually started much earlier. I didn't start writing it much earlier, but I started lining up things earlier. So I asked for letters of collaboration a month ahead. I don't remember how many letters I had, but between 3 and 5. And so that made it less embarrassing to ask last moment for a letter of collaboration, and also made me think, okay, which direction is this proposal going to go? If this is my collaborator, then, or rather, if I'm going to have this strong fabrication component, I need a letter from someone in our clean room, and so on. Another thing that was crucial to having some accountability was lining up colleagues who are going to read different parts of the proposal. And so I knew that I would first write introduction, so I aligned someone for that 2 weeks ahead. And I knew that the educational component is going to be closer to the end of the deadline, so I lined up someone a week before I was going to submit it. And at the same time, clearly you need to work with the university to actually submit and get an approval from the campus level. So all of those things I asked ahead of time, hey, can you read my part of application in a week or in 3 days, and so on. And that kept me accountable because I had to deliver something to someone. Another important thing was to ask for specific feedback. Hey, this is the first draft. Does this make sense? Hey, this is almost the final draft. Can you find any anything that doesn't sound good, or some typos even. So that's also really important to tell the reader what they're looking for, what the detail of feedback you're looking for. Right, so now we go to the advice page, and that is, first and most important thing is offer to program managers to sit on their panels and be a reviewer. This is the best educational experience because you can see how it's all made and decided. Who sits on the panel? What do you yourself notice when you're reading other people's proposal? What do other people notice? What syncs proposal? And so on. So I would say that this is the best way to have a different perspective on what you're writing. And this doesn't need to be just for career, it would be for any other NSF proposal. Then think about, why is this project career worthy? Could it be just another project, or is this something that when you get your tenure, you could say, hey, I got my tenure because I showed that this project is possible, or findings of my project actually made a difference. So also something that is not too collaborative, because this is an individual project. So figure out what is that and where you have the strongest background in your PhD or postdoc to actually carry out that research. Then think about who's the competition, because the questions that often arise are, why would this junior person work on this project when there's this senior person at another institution working in the same area and could probably do this faster because they already have experimental setups or the code developed or trained students and postdocs. So find something that other people are not working on, or at least some segment of it. Then think about what's the impact. Why would National Science Foundation care about your project? And make sure there is a fundamental scientific component to it. As we mentioned in the previous slide, who are the collaborators? And ask for letters on time. That can really get you into the mood of writing when other people start contributing to your proposal. Email the program officer as soon as the call is out. Send a one-page summary of your proposal and ask for a phone call. So the questions to ask are, is this within the scope of your program? Do you have any advice on how to make it better, streamlined for the panel, and so on? So yeah, you can get a lot of useful feedback from a program officer. Then ask someone who got a career, or someone who's working at the university with people writing and getting career awards, or other friends, peers, colleagues who are currently applying for career and are thinking a lot about career award, to read parts of your application. And think about in field and out of field. So, abstract, introduction, and then the research part, maybe you want someone who is closest to your field. An educational section, someone who has experience with education. So try to line those people up and ask them specifically what type of feedback you are looking for. And so that is it for my presentation. I wish you a lot of luck with your applications. If you have any questions and would like to reach out or see what my group does, my coordinates are at the bottom of the screen. Thank you very much for listening to my presentation.